Hi, everyone. I'm Ian Douglas. I'm a senior developer advocate at Postman, and I'm going to discuss some different API architectures comparing REST, asynchronous APIs, and gRPC. The agenda that I'm going to follow, we're going to look at some background on RESTful standards and how that came to be. We'll look at event-driven APIs like asynchronous. We'll talk about WebSockets and webhooks, and then we'll get into low latency performant APIs like gRPC. So REST was defined in 2000. And RESTful came shortly after that. Although there's no easy way to determine when that term itself came to be, it basically happened because people didn't like following the strict rules of REST. They liked the idea of what a REST API was, but they still wanted some amount of flexibility. And so they started building their own sort of mechanisms. We are seeing a lot of schools teaching about RESTful APIs, although mostly on the consumption side. Postman does have a student program where we work with schools to get students using Postman and learning about other API architectures. So what does REST even stand for? Well, it stands for Representational State Transfer. Let's break that down a little bit. The idea of representation is that the way we call the API is a representation of the action that we want to take on a resource like fetching or deleting data. State is basically needed because HTTP as a protocol, it's been around since 1991, but it's what we call a stateless protocol. It doesn't remember from one connection to the next what you did last time. And so every new connection, we have to tell it again where we left off, what we need to do. And so we can mimic state using things like sessions and cookies and things like that. But we basically need to provide this information on every single connection. The idea of transfer here with RESTful APIs is also that it's typically a single transaction communication. It connects to the server, it sends a request, it gets one response, and then disconnects. The next time it needs data, it has to make that connection, send a single request, get a single response, and disconnect. And it's a very repetitive, chatty mechanism. But REST quickly outgrew other popular protocols like SOAP. The simplicity of it was pretty easily understood and allowed for easy data packaging using things like JSON schema. It was more adaptable because it was human readable. It's also a lot more scalable, especially on the server side, allowing for easier expansion and creation of microservices. For the flexibility, for better or for worse, it was kind of wild territory out there for a long time with everyone trying to define their own idea of a standard for their own company. It's something that we now call governance in the industry that basically says this is how we want our APIs to behave. This is what we want our responses to look like across all of our APIs. As popular as it has been, RESTful APIs have been a little bit stuck in HTTP 1.1 territory and really needs to keep up with newer technologies. Companies like Google started introducing new protocols like Speedy, which was the basis for HTTP version 2. HTTP version 1, as I mentioned, clients connect, they do a single action, and then they disconnect. But also servers can't interrupt a client. So for example, a client could connect to a server and say, I want to send some data. And the server says, sure, start sending as much data as you need. And the client could send way more data than the server can actually handle. But it's not until the client says, okay, I'm done, that the server can then respond and say, wait, you sent me too much data. I can't even handle what you've sent me. And now all that data is lost and that data was transferred and you're spending money on bandwidth. And so we needed some improvements here along the way. The other big problem with RESTful APIs is what we call overfetching and underfetching. And the idea here is that when a client makes an API call, it's getting some amount of data back. But me as the developer of that API, I have to kind of guess what information you're looking for and what kind of information you want. And so I send back a payload of data hoping that that's what you want, but there may be too much data. There might be a bunch of data that you end up discarding, or there might be a crucial bit of data that you need, and now you've got to make another API call to go get that missing piece. But that other API call might be sending too much data as well. So we started seeing technologies like GraphQL come on the scene, which allow the client to specify, hey, when I take this action, I want to get back this exact data as part of my response. This could happen with REST by passing extra parameters, but then you're increasing that complexity a lot of your RESTful API. So can we fix this? Could we just move RESTful APIs to HTTP2 and just fix some of these problems? Well, it's not just a software change in your API, it's a whole infrastructure change that your DevOps team would need to support as well. HTTP2 is binary only, so you can compress your data. Um, it uses compression by default and uses encryption by default. But HTTP, at the end of it, still disconnects afterwards, and clients and server are still, um, it's still the single connection transaction kind of thing. There's no way to push event-driven data. And HTTP2 front-end adoption is still a little bit low. We do see it supported in JavaScript fetch, but most data transfers are still just sending text-based JSON data. So let's talk about some event-driven APIs and how we can improve on top of REST API. So the idea of async APIs is that they're event-driven. And there are two classic methods of async APIs that we call webhooks and WebSockets. These are still HTTP-based, so they still make a connection, transfer some amount of data, and then disconnect. WebSockets, unlike RESTful APIs and webhooks, can keep a connection open for a long period of time, alerting either side with packets of data when events happen. We see this most commonly in chat mechanisms where users can connect and get real-time updates when someone writes a message, for example. But developers don't necessarily need to pause and wait for a response before continuing their work either. Event loops like promises and other mechanisms called async await allow developers to choose when to pause execution of the software or when to wait for a response or not. For example, I can send a request saying, go handle this information, go handle this resource, but I'm going to continue working over here, and I might check back later to see if there was a response, or I may not even care that there was a response. I can just send that over and forget about it. Most typically, we see webhooks used in a response mechanism. For example, someone pays an invoice with PayPal. PayPal can call a webhook that you specify that can take some other action, like updating a CRM system. As mentioned earlier, WebSockets are commonly used for more real-time applications where you need to hold that connection open and have a conversation. There may be some amount of state exchanged every time you connect or reconnect to resume where you last left off, such as which message did we see last time for a real-time chat mechanism. GraphQL also has included a streaming data mechanism they call subscriptions. It's a bit like this publish-subscribe pattern, which we sometimes call pub/sub. There are other choices here, including a newer mechanism called server-sent events, where servers can push new data to a client, again, because these asynchronous channels are being held open. Asynchronous still has some problem areas, though. It can be harder to design and plan since you don't know which events are happening in any particular order. So you might need to reconcile data on either end of the connection to ensure that everything was completed. Webhook mechanisms need to ensure that whatever system is calling it can actually route to that server, which is tricky with trusted internal network mechanisms. There are other issues that you can run into, including rate limiting and throttling data that can also be more challenging with async. I'm going to pause on this screen for a moment if you want to pause the video so you can take a look at some of the primary differences between RESTful APIs and async APIs as far as the data transfer mechanisms, design complexity, use cases, and so on. Let's talk about some API performance and some things to take into consideration when we need to take things kind of the best out of our RESTful APIs as well as async APIs. We could, of course, just scale our hardware and add more systems to handle our load, and that will help with a little bit of performance, but that does raise other concerns and problems, especially with the cost of cloud computing providers. So how can we combine the best of the API architectures that we've mentioned so far, like controlling our data, handling streaming data, compression and encryption by default? What if there was an API type that gave us the flexibility of that single request response like REST, or the ability to stream data in either direction from client to server, server to client, or both in both directions, and also allow those connections to stay open for long periods of time, and also giving you a major performance boost to speed while minimizing your data throughput. Does that sound too good to be true? Well, gRPC was developed by Google in 2016, and it's built atop HTTP version 2. and it's the HTTP version 2 that allows for the long-lived connections similar to WebSockets and utilizes that binary-only approach by default. It's still a work in progress. There are not too many public-facing gRPC APIs out there, but we at Postman, we are seeing some growth here. gRPC has 4 data transfer mechanisms. The first is very much like a RESTful API where you connect, you make a single request response, and disconnect. You could use this like a WebSocket mechanism. The others are a combination of the client wanting to stream many bits of data to the server, or the server wanting to stream many bits of data back to the client, or allowing for streaming in both directions. The idea of streaming here is that you can send multiple requests or responses at any time as events occur on either end of the connection. gRPC is typically 7 to 10 times more performant than RESTful APIs, mostly because of HTTP version 2, and allows for a lot of communication back and forth between client and server before disconnecting. Adoption of gRPC is low, but we are seeing growth here. At Postman, we're mostly seeing gRPC APIs happening within internal networks to communicate server to server, and not so much from an end user client like a browser. Because it's based on HTTP version 2 and using protocol buffers to transfer that data in binary format, you do need some proxy libraries in JavaScript to communicate with gRPC from a browser. We will see improvements here over time. HTTP2, as an aside, has its own issues around denial of service attacks and security issues, which are being addressed in HTTP version 3, which is already out, but HTTP2 isn't even well adopted yet. So there may be more changes to gRPC and async APIs over time as problems with HTTP version 2 get addressed. And as time goes on, the tooling around gRPC will get better. gRPC is definitely worth the time to investigate as a feasible solution for minimized latency in the data transfer alone. Again, I'll pause here so you can see some of the differences between RESTful APIs and gRPC APIs. gRPC APIs have a lot of commonality with async APIs, but also give you that extra performance boost. So the big question is, can't we just implement a RESTful API on top of HTTP2 to gain some of these benefits? Well, yes, you can if you want to build it. GraphQL is a bit of a mix of REST and gRPC. It has the JSON payloads that are human readable, and they now have this subscribe process, which is a little bit like asynchronous as well for subscribing to when events happen. It can receive data over time. Could we just use a binary data format in REST that enforces data types? Well, absolutely. You just have to make sure that every client that connects to you knows exactly how to handle those messages. If you don't have a native software development kit or SDK available in the language that your users are going to be using. gRPC does have a discovery mechanism built in that can allow clients to learn about the API message payloads, but gRPC, you generally also have to share a proto file, that we call it, that sort of tells the client and the server what those message payloads are going to be. So going back to REST, could we just implement an event-driven architecture using REST? Kind of, but it would still be a single request response cycle because of HTTP version 1. And mimicking a stream of data is possible. That's how we've managed streaming content for a few decades now. Could we do encryption by default with REST? Yes, please. Please encrypt your data by default. But when we think about having to implement all of this, you've just increased the complexity of your API design quite a lot. You've just made your deployment and your management more complex, and you've likely made your infrastructure more complex. So is that really worth it when these other API architectures already do this for you? So now that I've thoroughly confused you with all of this, we can ask the big question, how do we choose what kind of API to build? Well, choosing an API architecture is a tricky balance of performance, but what does performance even mean? When we think about the evolution of HTTP version 1 and version 2 and the improvements that were made, and looking ahead to some of HTTP version 3's performance is going to be interesting. For example, HTTP 2 suffers from a latency problem where all transactions to the server stall if any one TCP packet gets dropped or reordered. And because the internet is what it is, we can't always guarantee that all packets from me to you are using a single communication line. Everybody who's connected to that server feels the lag. HTTP 3 is based on a new protocol called QUIC, and it's based on UDP, which will reduce some of the communication chatter. It's going to have new session management built in to mimic stateless calls while still retaining the familiar HTTP methods, headers, and status code systems that we've been using and that we're all very familiar with. It's actually been supported now since 2020 and 2021 in most major browsers. In fact, most client libraries are now fully supporting HTTP version 3 as well. But performance really comes in two different forms. There's team execution versus the software latency. I'm a huge fan of learning something new, but does your team already know these technologies, or are they going to have to go learn something brand new? Does your DevOps team have to go learn how to build some new infrastructure? Do your teams already know how to consume that kind of API or handle event-driven architecture? Is there an easier migration path for performance later without a total rewrite? These are things that need to be taken into consideration when we think about performance, because performance isn't just about the software. It's also how quickly your team can implement these changes. So I hope this was helpful. I hope the constructive comparison between REST and async and gRPC was helpful. I'm happy to answer any questions that you have. My username on most social platforms, including LinkedIn, is IanDouglas736 if you'd like to reach out to ask any further questions. And a big thank you to API Days for having me today.